All right. Let's get started. Number one. Number one is dealing with what we talked about yesterday. We didn't quite, I don't think we went too in depth into it. We will go really, really deep into rotating things about the x and y axis and different axes. Okay. In fact, well, let me grab this one. So you have y equals x squared, which is a parabola, right? And we're taking that parabola from 0 to 3, and we're revolving this curve around the x-axis, right? So can you visualize kind of the shape that it makes? A raindrop? It's kind of like a cone, but it's caving in. Kind of like the lance, a lance on a knight's, yes, lance, yeah. Okay, well anyway, so it's going to revolve, it's going to duplicate on this side in a sense, and then we're going to get a circular shape there, right? Okay. Now, we are approximating, because we don't know how to find the volume of that yet. We will learn, okay? But we're approximating by doing 3 subintervals. So how wide is each subinterval? 1, because what do? We take the total subinterval and divide it by 3 subintervals, or the total interval divided by subintervals. So each one is 1 and 2, I guess, right? And so we kind of get 2 more circles, in a sense. So you have kind of the cone here, and then part of the cone, and then part of the cone. You guys see that? Now, again, we're approximating using, instead of rectangles now, what shapes are we using? Because as we rotate that rectangle around, we get a cylinder, right? So maybe the better version of this would be something like this. And then like this. So it's almost like a cake. Can you see that? Yeah? Okay. Now, how tall is each cylinder? Again, we're looking at it sideways. These are each 1. And the radius of each cylinder is the distance from the center. What represents the center of this shape? The x-axis, right? So what represents the radius? The y values, right? Now, are we doing a left, a right, or a middle? Right. Okay, so that means in this part, in this piece only, which piece are we using? We're using this height, right? So how do I get this height?
You plug it into the function.
I plug it into the function. So how tall is it?
1.
It's 1, right? And then out of this one, so here's the cone here, we're using the right-hand side. So this, I guess. So it's going to be, 4, because we're plugging in 2. And then this one is going to be 9. Okay? So now the volume, actually the volume of the whole thing is approximately, how do I find the volume of a cylinder? So pi, what's the radius of the first cylinder? So 1 squared times 1. Plus pi times, what's the radius of the second one? So it'd be 4 squared times 1 plus pi times, wait a minute, hold on. Yeah, 9 squared. Christina, did I tell you something wrong? I'm sorry. I forgot that we were squaring the radius when we were done with it. The radius is the x squared, and then we have to square it. I'm sorry. So volume equals, that would be pi plus 16 pi plus 81 pi. So that's going to be 98 pi. Are you okay with that? So the volume of the cylinder is pi r squared h, right? the radius is determined by the equation y equals x squared. So we found the radius, this distance, by plugging in 1 to our equation, which is 1 squared, or let's use this one. 2 squared is 4, so the radius is 4, and then we have to plug in the 4 to square it. So you're kind of squaring twice. Yeah, okay. Are we good with this? No as in I need more time, and no as I don't understand. Huh? Erica, I don't understand you. All right. Number 2, we are looking for the derivative when x equals 1. So you could solve for y. That wasn't my intention, but it's fine if you do. What rule would we be using to find the derivative of this if we don't solve for y? What's it called? Chain, but there's a word for it. Implicit differentiation. Chain's a word too, yes. Implicit differentiation. Remember taking the derivative of y in respect to x. So what's the derivative of x? Or x cubed? 3x squared. Because x is a what in this case? X is the variable and y is the function. Okay, so what rule do I have to find the derivative of 2xy? Product. So what's the derivative of the first thing? 2 times the second thing plus y prime times 2x. And that equals 0. Now I'm looking for y prime. I'm looking for dy dx. So I need to know what x and y are to find y prime, right? So you could move it all over, and that's fine. I don't want to, but let's plug in what we know. We know x is 1, so we're going to say 3 times 1 squared plus 2 times, what's y? We don't know. We've got to find y by plugging it into the original equation. So if x cubed plus 2xy equals 9, we're going to say 1 cubed plus 2 times 1 times y equals 9. And then we get 1 plus 2y equals 9. So 2y equals 8. So y equals 4. So we can plug that in here. 2 times 1 equals 0. What was the question? No.
But the last time we did a warm-up problem like that, you said we could leave it in terms of y.
But you didn't specify.
If I'm just asking for dy dx in general, the function or the equation, then that's fine. No, it says what's dy dx when x equals 1.
But I'm not wrong. Like, that is dy dx.
But by you writing it that way, you're implying that y could be anything. And it can't be because x guarantees a certain y. Sorry, you lose a point. So y prime equals negative 11 halves? All right, there it is. Okay. Okay. Okay, so today is kind of the introduction to what we call an integral. Good stuff, let me tell you. I'm going to explain it. Okay. The definite integral was the title. Okay. All right. The definite integral. The definite integral. As opposed to the indefinite integral. All right. So, what have we been doing lately? We've been taking the area under a curve with a given function, right? And we've been trying to estimate the area under the curve by doing what? Approximating it by cutting it into rectangles, right? And we know how many rectangles we want to cut it into because I tell you how many subintervals. But how many rectangles do we really want to try and get out of it? Infinitely many, right? So those were called rectangular approximation methods. That's why it was RRAM, MRAM, and LRAM. But there's another name for it. It's called Riemann sums. No, his name's Sum. Yes, it would. Okay. So, yes, some guy named Riemann developed this. Okay. Again, these are only estimates. They don't give you the exact values. And I wish I would have had the program in my calculator from yesterday. But Gil downloaded one on his phone, and you could see the graph, you could see the curve, and you could see all the rectangles. And the more and more rectangles you added, the more you can visualize that the gaps were disappearing. Can you see that in your head? No? You'll see it today. You'll see it. I do have a graph of it today, okay? So we can write it like this, okay? Area equals. What is that thing? Have you seen this somewhere in the past? A little bit? This is called summation notation, okay? Epsilon. Is that the letter, right? Epsilon. Okay. So the area is approximately that thing, and I want to analyze this a little bit here. Okay. We see f of x times delta x. You probably did something like this in a mixture of Algebra 2 and analysis. Okay. Okay. I'll define what everything means up here. But look, f of x, remember, we're basically trying to cut things into rectangles. And so each rectangle, what's the area of a rectangle again? Base times height, or length times width, however you want to express it. But what represented the base of the rectangle? Not the x value, but the distance from one x value to the next x value, right? What do we call that? We call that the change in x, right? Think about slope. What's the distance from this x value to this x value? It's delta x. Remember that? Yeah? Maybe? Okay? That's what the delta x is there. That's the width of the rectangle. And what gave us the height of the rectangle? Whatever the y value was. And we get the y value from f of x. So when you see f of x times delta x, that is just the area of one rectangle. You got that? Okay. The sum thing, the epsilon thing, means sum. It means add up all the rectangles. Right? I'll get there. I'm going there right now. Okay? So how many rectangles do we have? However many I tell you, right? Right? Cut it into 3 subintervals, you have 3 rectangles. Well, n represents the number of rectangles. Okay? N represents the number of rectangles. And k equals 1 means you're starting at rectangle number 1. Okay? Well, depending on how many I ask for, right? Now, the idea, to get exact, is, yeah, you're going to go infinitely far. Okay? So maybe write it down. F of x is the height of each rectangle, and of course the height changes depending on where you are at on the curve. Okay? What did I say delta x was? The change in x, but what did it represent in what we're doing? The width of the rectangles, right? So delta x is the width of each rectangle. And then n is the number of rectangles that we're trying to work with. Okay? Number of rectangles. You guys got that? It's good stuff. So here's a curve. This is the first time you've seen a curve go below the graph when we're talking about this stuff. We're going to talk about that a little bit. So where do you think I'm going to ask you to start to take a rectangular approximation? A. And I'm going to ask you to go to B. So how far is the whole interval? B minus A, right? That is our total interval. So if I said go from 0 to 7, how big is the interval? 7, but that's only because I started at 0. What did I really have to do? Subtract, right? And there will be times where I say go from -2 to 5. How far is that? Because 5 minus -2, right? Okay, so in this case, I just drew lines there. How many rectangles do I have? This one's kind of weird. It's actually, if we're trying to cut this into equal subintervals, we have one rectangle here. We have one here where part of it is below and part of it is above. Then we have one here and one here. So how many rectangles? We have 4 rectangles. Okay, and what kind of Riemann sum am I doing here? A midpoint, right? Because the height of each rectangle is based on the middle value of each rectangle. Is that okay? Okay. So I say n equals 4 because n represented the number of rectangles. And we don't have a function's value. What is delta x? How wide is each rectangle?
1/4.
Good. Good. So remember, what do? We took the total interval and did what with it? You divided by how many rectangles you wanted, right? So in this case, it would be what? B minus A divided by 4. Okay? Or what was the 4? N was the number of rectangles, so I just put n up there. In this case, B is 10, right? And A is 2, so what's the whole interval? 8, because you say 10 minus 2. B minus A is 8. And then divide it by n, which is the number of rectangles you get. You get 2. Whoops. 2. Are you guys okay with that? Based on the picture. No. Based on the graph. So, all right. First of all, let's use the graph and say each one of these squares is 1 unit. Okay? So A is where I start and B is where I end. So how do I figure out the distance between them? I subtract. And then, so we would say B is 10 because I just counted the squares. A is 2. So the total width is 8. And then I divide it by how many rectangles I have. And in this case, I just observe that in the graph. So 8 divided by 4.
How do you make them 4? Did you just choose to just take that rectangles, or?
Yeah, basically. So my example is I cut it into 4 rectangles. That's all. Just because I did. All right. Okay. Any more questions? Yeah, most of the time I'll say cut it into 10 rectangles, cut it into 3 rectangles, whatever. Then you'll know.
So you made up the B and A value, B minus A?
No, I observe the graph.
Okay.
A is 2 and B is 10, just by counting. Okay? All right. Can I go on? But again, the goal is not just to approximate. Unfortunately, we're sometimes left with approximating because in life we aren't given functions that represent what's going on in real life. We're given data. We're given what? What's data?
Data is
Like
A bunch of points, a table, right? Okay? So we can only approximate using rectangles in that case. But if we're given a function, we can find the exact area under the curve, or the exact whatever application you want to apply. Okay? So in order to find the exact area, what do I have to do? I need to make the rectangles infinitely thin. Yeah, because it says so, right? Okay. But in terms of calculus, this is what it looks like. You go, what? We're taking the limit as the change in x approaches 0. Remember, what did delta x represent in the rectangles? It represented the width of each rectangle, right? And the less and less the width is, the more rectangles I'm getting. And the more rectangles I'm getting, the more accurate I'm getting. Okay? So put your pencils down for a second. Pay attention to this graph because this might help you. Okay? Based on what I had before, how many rectangles do I have right now? We have 4 rectangles. And how wide was each one in the previous frame? They were 2. So this length here represents delta x. It represents the width of the rectangle. In order to make delta x get smaller, I need to add more rectangles. So delta x is now that length. And I'm going to keep cutting it and cutting it and cutting it, and now delta x is that length. So what's happening What's happening to delta x? It's getting smaller. And as delta x gets smaller, what do we see happening to the number of rectangles? It's getting larger. So what could we say? As delta x approaches 0, the number of rectangles approaches infinity. And what letter represented the number of rectangles? N. So we could say this. As delta x approaches 0, n approaches infinity. So how could I rewrite that area function, or that area summation, in terms of n? Yeah, so it's the same thing. It would be the limit as n approaches infinity of the sum of f of x dx. Ah, we talked about that before. Remember, remember, delta is the capital letter delta, right? It means change in, right? That is the lowercase delta. So it's the little change. And we want little change because how much do we want delta x to be? Really, really small. Really close to 0. Does that make sense? This is called the definite integral. Okay? As you take the limit of the sum, in other words, as you add more and more rectangles, as the width of those rectangles gets smaller and smaller, can you kind of see how the accuracy is improving? The accuracy of the area is improving, right? So as the number of rectangles goes on to infinity, we are getting the exact area. And that exact area is called the definite integral. That's important. This is a term you need to know. Okay. So that's the definite integral. Now, with that said, let me take one step back here. With that said, we are not going to be dwelling on sigma notation very much at all. They rewrote the standards this year for the AP exam, where I can almost guarantee they'll have one question that has the sigma notation in it, and we'll evaluate how to translate that into the notation that we're really going to be working with. Okay, and that's what this frame is for. Calculus doesn't use sigma notation for the basic part of calculus. It uses what's called the integral, the integral symbol. I find it way easier. The integral is way easier than the sigma notation. Okay. So same graph. You get something that looks like this. Okay. So we would say the integral of f from a to b, in other words, the area under the curve from a to b, is written like this. Okay. You have don't just write an S. My S doesn't look bad. That's what it is. You don't say S f of x dx. Okay? No. It's an elongated S. It's okay?
Oh, and then in the text, the ends are really big.
I don't know. Go ahead and spend your time being detailed like that. I'm sure it's just the font. So we have to understand what this means, and it's actually very simple to understand. Okay? What were the pieces of information we needed in order to figure out the area under this curve? You needed to know the number of rectangles, sure, but remember, the number of rectangles ultimately, if we're trying to find the exact value, is what? Infinitely many, right? So that's not a concern anymore. We needed to know where we're starting, and we need to know where we're ending. But wait a minute, you guys say the change. How big is the change going to be as the number of rectangles approaches infinity? It's approaching 0. So that's irregardless too, because that's the same in all of them. We need to know where we're trying to evaluate the integral from. We need to know we were looking for the area under the curve from this point to this point, right? So what is the starting point here? A, and what is the ending point? B. So in this equation, you have the elongated S, the integral symbol. A is where? On the bottom. That's the starting point. And b is on top. That's the ending point, right? What does f of x represent? The height. And what does dx represent? The small change, which is technically, well, hypothetically 0, right? So here's the terms we're going to use. A is the lower bound. That makes sense because it's on the bottom, right? Yes? Okay. And b is the upper bound. And that makes sense because it's on top. F of x is called the integrand. The integrand. And dx is the variable of integration. You know how when you said what were the different ways of writing a derivative? You could say y prime or dy dx, right? Remember, y represented the function and x represented the variable that we're taking the derivative in respect to, right? Well, it's the same type of thing here. Dx tells you you're taking the integral in respect to x. But it also tells you, remember, going back to what this actually is, we're finding the area of rectangles, right? Right? F of x represents the what in those rectangles? The height. And dx in this case represents the width. Okay, so that's what it means in terms of the area. Okay, so you can read it like this. We are summing, that's why it's an S, we are summing the f of x times dx. We're summing the area of the rectangles where the height is f of x and the width is dx. Does that make sense? You're all like, yeah, I'm just going to shake my head yes, but I have no clue what you're saying right now.
You don't use the numbers in A at all when you're like looking at something?
We will. We will use them. Okay. You're saying f of x times dx is the area of the rectangle. We are summing the area of the rectangles where the rectangles start at A and end at B. You guys got that? Okay. So let's take a look at this. An example. Evaluate the following. And this looks really scary right now. But it's not that bad. What is the lower bound of our integration? -2. What's the upper bound? 2. So essentially, what is this question asking you to find? There it is. We're trying to find the area under the curve from -2 to 2. So, if we're trying to find the area under the curve, it might be a good idea to graph the curve. Do you guys recognize that equation? It's a circle. Semicircle, right? With a radius of 2. Centered at 0, 0, right? Okay. So let's graph this. Okay? So like I said, it's a circle. Semicircle with a radius of 2. So I'm going to graph it. That's the graph of the function. And why does it go back to -2 here? Instead of -3 or something like that? Well, that's what, this is saying we're trying to find the area between -2 and 2. But why does the circle go to -2? Because the radius is 2. How did you know the radius was 2? Because it's the square root of that value right there, 4, right? And it goes to 2 because, again, the radius is 2. So, again, what is this asking me to find? The area under the curve from -2 to 2. So we're trying to find the area from -2 to 2. That should be easy. How do you find the area of that shape? It's a semicircle, so the area is 1/2 pi r squared. And the radius in this case is 2. So our answer is 2 pi. And we're done. Okay, let me do this. I want you guys to, I'm going to give you like 30 seconds to discuss this. If I changed it to this, try and evaluate that. But talk about why it is what it is with somebody around you. So what's the difference in the two problems? we're still dealing with the semicircle in the equation, right? What was this thing called again? The integrand, right? So we're still dealing with this function, this semicircle, and the semicircle goes from -2 to 2, but this is saying I only want the area from 0 to 2, so I'm only looking for this guy, which is a quarter of a circle, right? So the area is going to be 1/4 pi r squared in this case. So that's 1/4 pi times 2 squared, which is just pi.
How'd you get to further radius?
Because in the equation of a circle, this represents the square of the radius. Okay? All right. So there's our final answer there. Okay? Any questions on that? None? Now, what shapes do you know the area of? A circle, a rectangle, because we've been doing that, a triangle. All right. So again, we're learning right now how to solve this graphically. So let's just keep it simple. What kind of function would give me a rectangle? Come on, if I say find the integral from 0 to 3 of a function of the integrand dx, what would the integrand have to say so the shape looks like a rectangle? A constant line, right? Okay? So if it said something like this, 5, right? Okay. Well, let's do that real fast. 5, and we're going from 0 to 3, right? So what is the integral from 0 to 3? In other words, what's the area under the curve of the constant 5? 15. Done. Yes, but I'm just showing you what this means, okay? Now, what would it take, what kind of function would it take to make, let's say the same limits from 0 to 3, to make a triangle?
Negative linear.
Maybe.
So, yeah,
Like that? Okay, so let's say this is 3. What would the equation be? Absolute value, we don't want to do that. Skip them. Negative 2x? I don't know. You're getting a little bit complicated, but that's a good thing. Negative 2x, which would mean what? What is this point? 0 is the x value. What's the y value? That doesn't work. That's not that equation. Negative 2x is that. Jeez, Shelton. Whee. So what would this equation be? Negative 2x plus 5, let's say. Okay? Say it again. 2x. Okay, I'll look at that one in a second. So what is this point here? 5. So how would I find the integral of this equation? Oh, wait a minute. Does it actually hit at 3? When x equals 3, what is this? Negative 1. Yeah, I don't want to do that yet. We're not there yet. Let's do this. Let's do this. Just for now. Negative x plus 3. What's the y-intercept then? 3. What's the x-intercept? If I plug in 3 for x, I get 0. So that's the integral from 0 to 3. That's what we have, right? We're looking for the area under the curve because we're looking for the integral from 0 to 3. So how do I find it? 1/2. What's the base? 3. What's the height? So that would be 9/2 or 4.5. Okay. Erica said, how about 2x? Let's do 2x. Okay, fair enough. What's 2x look like? With a y-intercept of? Something like this? So from 0 to 3, we're actually looking for this triangle, right? So that's going to be 1/2. What's the base? 3. Now what's the height The height is this length, right? Why is this 6? Because we plugged in 3 to get our height, right? So 6, which is 9. You guys okay with that? The integral. The definite integral. All right, here's maybe a little bit of a twist to scare you. You've already scared me enough. 0 to 3 of 2x plus 1. Just that little plus 1. What do you think? Graphic, come on, it's a line. That's not hard. Go up 1, and then go up 2 over 1. I don't care about the 1, though. I want to go over to what? 3. So how high is it going to be? 7? Okay. So the line looks something like this. 7, right? What is that? You could think of it as a rectangle and a trapezoid at this point, but you've got to know the formula for area of a trapezoid for later on. Okay? Does anybody know the area of a trapezoid? Wait, shh, what? You can cut it into a rectangle and a triangle, and that's fine. If you want to, what would the area of this be? 3, because that's 3. And what would how tall is this? 6. 6 times 3 is, so that's 9, right? And so 12. But that's not my intention. Does anybody know without looking at the chart what the area of a trapezoid is? One half B1 plus B2 times height. 1 half. What does bases mean in a trapezoid? It means the two that are parallel. So normally we see a trapezoid like this. This trapezoid is doing what? Right. So base 1 is this. What's base 2? And now what's height mean? It means the perpendicular distance between the two bases. So 3. So that's 1 half of 8 times 3, which is 12. Same answer. Are you guys okay with that?
Yes.
All right. The signs of the integral, it's pretty basic, but remember in geometry, what could you say the answer to the area will always be? Positive. When you get to calculus, it's not. Now, wait, let me rephrase that. Area is always positive. But on an integral, on a graph, when the area is below the x-axis, if the region is below the x-axis, then the integral's answer is negative. The area is still positive, but the integral is negative in that region. Okay? Okay, so the signs of integrals. If the curve is above the axis, then the integral is said to be positive. Okay? And then vice versa. If the curve is below the x-axis, then the definite integral is negative. So, here's an example of the graph. We can say that the integral from 0 to a is positive. What else can we say? That the integral from a to b is negative because that region is below the x-axis. And then we could say the integral from b to c is positive. So what do you think the integral is over the whole thing from a to c?
Negative.
Why negative?
Because positive, negative, positive.
Well, you're not multiplying here. What are you doing with those areas? You're adding them together. So there's the comparison. Is the region above greater than the region below?
Oh, yeah.
I don't know. It's pretty close,
Wait, is this the only
right?
slide